Hi, myself Yuvraj. So now I will show you one block diagram. This is power control in microgrid. So my intention, my aim is to explaining about the role of FPGA in renewable energy related applications. So for example, if you take this block diagram, you can find the DC to DC boost converter with the solar panel, and then DC to DC boost converter with the wind source, and then bidirectional buck boost converter with battery bank, and bidirectional buck boost converter with the super capacitors and some DC loads. And also this is the source side, and this is also source because of it's a bidirectional inverter. This is a 3-phase AC grid, and then 3-phase voltage source inverter, active rectifier, AC load, shunt active filter, like kind of setups. So upcoming videos I will show you the experimental setup of each and every blocks. Already I have YouTube link. I will share the YouTube link in the description about that wind source. In the wind source I used DFIG, so you find out the link. Okay, and then see the power flow here. The power flow can be controlled by the single FPGA. So how it is possible? Because if you are using different controller for different circuit, for example you have the microcontroller DSP 4011, you can able to code that DSP boost converter, and then for bidirectional converter also you can able to code with the single DSP controllers. But I'm using FPGA controller because FPGA has lot of applications and advantages, like for example it has the parallel execution, and also it has more number of IO lines. Due to that I can interface all the power modules, for example boost converter power module and bidirectional buck boost converter power module, because each and everything we have the IGBT switches or inverter switches, right? So that can be pulse can be fed from the FPGA. And also for example if you want to control the DC to DC boost converter, so here you need to use the maximum power point tracking control algorithm, because you must track full power from the PV source. So for that you need to take the panel voltage, panel current, and then output voltage, output current, because here also you need to maintain constant DC link voltage in that common DC bus. So from the voltage and current you have to do the maximum power point tracking control algorithm like P&O. After that you have to give voltage saturation for this, and then you need to apply the pulses to the boost converter. Based on that, this boost converter can be boost the voltage. For example here if you are using 100 volt panel, here if you are maintaining 300 volt, means the boost converter will operate based on your maximum power point. And for wind source also the same thing we can use for maximum power point from the wind. So the wind can be converted into rectifier, DC by the rectifier, then it given to the boost converter, then the output can be converted in the common DC bus. And here we have the battery bank. This is a bidirectional buck boost converter. The role of bidirectional buck boost converter here is, so whenever the power need to stored in the battery bank, it will act as a buck converter, the power flow from common DC bus to battery. So whenever the power need to this common DC bus, at the time the power can be feed from battery to common DC as a boost converter. So it will act as a buck and boost converter. And also we are using the battery, so we need to find the SOC of the battery. Based on that we have to do some algorithm, and we have to do some battery management system we need to do. So that also can be programmed through FPGA controller. So if you are using parallelly the DC to DC boost converter MPPT, and also DC to DC boost converter in the wind source, and then battery bank power flow, power management in the battery, so nothing is affected by this. For example, there is no interruption between these two controllers because it's a parallel execution of FPGA. So one FPGA can run this block separately, and then run this application separately, and run this application separately. So the super capacitor also we need to use, because based on this common DC link load, if the sudden changes in the load, the super capacitor will feed the power to this. So if sudden dip in the sudden reduction of the load, then super capacitor will get charged. Because battery, the sudden changes, if you are making the battery load, if you are consuming the power from the battery, then your life of battery will be reduced. So that we are using the SOC and all. So see the source side itself, all the power model like boost converter and then bidirectional buck boost converter can be controlled in single FPGA, but there is no effect of or interruption of these pulses to this or these pulses to this. So why? Because it's a parallel execution of nature. and also FPGA has more number of IO lines, so without any problem we can interface all the power modules. You can generate more than more than hundreds of PWMs, more than 200 PWMs you can able to generate. Okay, and also you can able to take the feedback. For example, here you are taking the feedback of solar PV panel voltage and current, and then here wind voltage and current, and then here in battery voltage and current you have to take, and then you have to find the SOC by the Coulomb counting method or whatever method you can do it, and then you have to do the current control, hysteresis control. So control technique also you can develop in the FPGA, okay, parallelly. So why? Because if you are using separate controller, there must be a fluctuation or power flow, some small ups and downs in the common DC link. Okay, if you are considering this side, you have the inverter, so bidirectional inverter which can be connected to the grid, 3-phase AC main. So here also we have the bidirectional nature, right? The AC can be converted into DC here, and the DC can be converted into AC and feed to the grid. For example, more power is available here, so it has to feed to load. Even though if we have the more power, then it is feed to the grid. So if suppose in night time there is no PV source, and for example less wind source, means the DC load is constant, because okay, if we made this DC load constant, then the power is coming from the grid to this DC. So that's why we are using bidirectional 3-phase inverter. Okay, and then these are all the additional component: 3-phase voltage source inverter, active rectifier, AC load, and then shunt active filter. So if you want this shunt active filter also, it is used to for inject the harmonic current and reducing the reducing the harmonics from the current source current and maintaining the unity power factor. So the every operation can be done in one single FPGA controller. Okay, so in upcoming videos I will explain you about the experimental setup of each and every boost converter, and then bidirectional buck boost converter and the inverter. So the common one FPGA, how it is maintaining the power management. For example, when power is low, more power is needed to the load, then how it is consuming from the battery or wind. So everything we have seen with the experimental results and with hardware setup. Okay, hardware setup and waveforms clearly we will explain. So and then later how to work with FPGA and how to operate all those models, what are the components can be used as a hardware. So it's a black diagram, so it's a just skeleton. So we'll see in depth in future upcoming videos. So please keep on supporting me and subscribe. Thank you.